Well, hello everybody, and welcome to a wonderful day of algebraic structures. If you recall, you will have a test given to you today as a take-home exam. It is already up on Blackboard in case you're wondering, except it will not be available till 3:30, so that you can't look at it until after class. And then you'll have to write it up and turn it in by Wednesday at midnight, much like you would an assignment. But the goal today is to go through a practice exam so that you know what to expect and how to write things up and what I want to see. Now I do want to point out that on last Wednesday we talked about Z2 cross Z4 and we did a lot of the same stuff. We found the subgroups of G, we determined the order of each element, we found the left and right cosets, and we found the subgroup lattice of the group G. And so just be straightforward. That's what your test is going to be, is for some group G, do those things 1, 2, 3, 4, 5. You notice that there's a number 6 here on the practice exam I gave you. I meant to delete that one, but I missed that that was still there. We have not talked about homomorphic images yet, so that won't be on the test. But you'll have to do exactly what this looks like, is 1, 2, 3, 4, and 5, except it'll be some other group. What group is it going to be? I don't know. You'll have to kind of figure that out and figure out what that looks like. But we'll walk through, and if you guys have questions along the way, make sure to ask or point things out. But we'll kind of walk through and just say, well, here's a group. What does it look like? Well, let's find all the elements. Then let's find the Cayley table. Let's find the subgroups, and let's find the order of every element, and work our way through all of these questions until we have a nice write-up analyzing all of the nice features of the group G that we've discussed so far in class. All right, so the first thing is, what does S3 look like? Well, S3 is, and now if you don't know the notation, you don't remember what that's talking about, remember this is a take-home exam, so you're welcome to look that up in the book and say, oh, that's a set of permutations on a 3-element set. So the set of permutations on a 3-element set are all of the bijective mappings from the set 1, 2, 3 to the set 1, 2, 3. Now we have different ways to notate that, and so instead of having to go through and talk about all those, I'm just going to say we've kind of done that a few times, so let's look at what that's going to look like. And there we go. I've already made the Cayley table for us so that I don't have to write it up at the board. I can just refer to this as we need it. But in permutation notation, we have the identity mapping. So 1 goes to 1, 2 goes to 2, 3 goes to 3. We have the mapping 1, 2, 3. So 1 goes to 2, 2 goes to 3, and 3 goes to 1. We have 1, 3, 2, 1, 2, 1, 3, and 2, 3. So there are 6 permutations on a 3-element set. So if we want to find the Cayley table to determine what the products are, or the compositions of each of these look like, we're going to have to make a 6x6 table and make 36 products in here. And we've done this together before, but I would suggest that's the type of thing that you could go back and look at some of the videos that we have where we say, okay, well, what is 1, 2, 3 composed with 1, 2, 3, or 1, 2, 3 composed with 1, 3, 2. And so if we do that, this is the table we end up with. Well, assuming I did it correctly. And so that's where you want to start. You want to say, what does my group look like? What are the elements? What does the product look like? Let's come up with a Cayley table. Now, as far as the group I give you on the test, it may be 6 elements. It won't be 7, because as we saw, a 7-element group would be a cyclic group, so that's a little too easy. So it might be 8 or 9 or 10. It's probably not going to be more than 10, because then you've got a 10 by 10. You'll have to calculate 100 different compositions or multiplications. But I could do that, but probably not anything bigger than that. So it'll be a finite group of a relatively manageable size, somewhere between 6 and 10. You'll have to be able to find all the elements and come up with a Cayley table. All right. Abel, you're talking about a time limit on the exam. The exam is a take-home type exam. I wrote it up so that you don't have a time limit other than the fact that it has to be turned in by midnight on Wednesday. So right after class at 3:30, you can start working on it, and you can continue working on it until you are done. And you can come back later and do it whenever you need to. It's going to be much like the assignments we've been doing, where I give you the homework problems and you upload them when you're ready. I thought 2 days would be enough time to get it done, unlike the assignments where I give you a week, because I didn't want to give you a full week to do the exam. I felt like we want to have a reasonable amount of time to do that, so by this Wednesday at midnight, I thought you guys could get it done. Thank you for the question, though. If there's anything else that comes up, let me know. Otherwise, let's go ahead and go to the chalkboard. I'll try to leave this up, and let's look at my group S3. So I wanted to find all of the subgroups. So if I want to find all of the subgroups, what I need to do is start talking about, well, what do those subgroups look like? And if you'll think back to last Wednesday, when I try to find the subgroups, I'm going to start off and say, well, let's find the cyclic subgroups. So all the groups generated by one element. So I would say the group generated by 1 is going to be equal to, well, 1's going to be in there. And then remember, for the cyclic ones, we closed these under multiplication. So we found 1 composed with 1 composed with 1. We also found the inverse and composed it both directions, the inverse multiple times. And so we closed it under compositions, then we closed it under identity, and then inverses, and then closed it under compositions again. And so that's how we're going to end up generating these groups, to start with one element first. Go through all of those, and then 2 at a time and see what happens. But if I start with just the identity, what is the identity mapping composed with the identity mapping? Well, I think I just get the identity mapping. And so this is closed under compositions. If I find the identity on this set, we know it's the identity mapping. We're already closed under that. The inverse of the identity is the identity. So we're closed under compositions, identities, and inverses. So this is the group generated by the identity element, is just the group consisting of the identity element. That one's not too bad. So if I look at my Cayley table, the next thing I had written up there was 1, 2, 3. So I'm going to find the group generated by 1, 2, 3. And so what I'm going to get is I'm going to start off with 1, 2, 3. And then I'm going to compose that with itself. So if I take 1, 2, 3, composed with 1, 2, 3, I'm going to start off and I'm going to say, okay, 1 goes to 2, but then 2 goes to 3. So I end up with 1 going to 3. Then I'm going to start with 3 and say 3 goes to 1, 1 goes to 2, so 3 ends up at 2. And then if I start at 2, 2 goes to 3, 3 goes to 1, so 2 would end up at 1. So I'd end up with the permutation 1, 3, 2. So I have 1, 2, 3, I have 1, 3, 2. So I should compose again. What is 1, 2, 3 composed with 1, 3, 2? Well, that's going to be 1 goes to 3, 3 goes to 1, so 1 goes to 1. Then 2 goes to 1, 1 goes to 2, so 2 goes to 2. And 3 goes to 2, 2 goes to 3, so 3 goes to 3. So I get those composed together as the identity. And then if I compose it again with 1, 2, 3, I get 1, 2, 3, then 1, 3, 2, then 1, then 1, 2, 3, 1, 3, 2, 1. And so if I keep composing over and over again, starting with 1, 2, 3, those are the only 3 I'm going to get. Now I should be careful and make sure this closed under compositions. Well, if I take these 2, I get this one, these 2, I get that one. So if I take any 2 of those, I am closed under compositions. I have the identity in here, so I'm closed under identity. And these 2 are inverses, and this is its own inverse. Therefore, I am also closed under inverses. So this is the smallest group containing 1, 2, 3. If I wasn't closed under any of those, I'd have to finish closing it by adding more elements in. But that would be the group generated by 1, 2, 3. questions on that at all? If I start with 1, 3, 2, I won't go through the whole thing, but you start with 1, 3, 2 composed with itself as 1, 2, 3, composed again as 1, and you get exactly the same group. So you would need to go through and see that 1, 3, 2. If I generate that, I get the same thing. But then you want to say you don't have to write the group twice. You just have this is one subgroup, this is one subgroup. You don't have to say this is two distinct subgroups because it's not. It's the same subgroup. And we just have it's either generated by 1, 2, 3 or 1, 3, 2. All right, the next one I think I had was 1, 2. So I'm going to take 1, 2. The group generated by 1, 2 is going to contain 1, 2. And if I compose 1, 2 with 1, 2, I get 1 goes to 2, 2 goes to 1, so 1 goes to 1. 2 goes to 1, 1 goes to 2, so 2 goes to 2. So I get the identity. So then I'm closed under compositions because I keep composing with 1, 2. I'm just going to get 1, 2, and 1, 1, 2, then 1, 1, 2, then 1. Now if I look at this, there is an identity in here, and I want to make sure I'm closed under inverses. So the inverse of 1, 2 is itself. Inverse of 1 is itself. So yes, this is closed under compositions, identities, and inverses. So the group generated by 1, 2 is just the set consisting of 1, 2, and the identity mapping. If we do the group generated by 1, 3, we get 1, 3, 1. And if we do the group generated by 2, 3, for the same reason, we get 2, 3, and 1. Now I know those are different, but if I follow the process I did here for these two as well, I'm going to get the same thing. So you'll notice that I went through each of the 6 elements of the group and found the groups generated by them. So I found the cyclic subgroups. And so we have 5 distinct subgroups. 1, 1, 2, 3, 1, 3, 2, 1, 1, 2, 1, 1, 3, 1, and 2, 3, 1. Now, I'm actually looking a couple steps ahead. I forget exactly where this one was, but I did ask for the order of each of the elements. So we can actually answer that now that we have the cyclic subgroups, and we could say the order of the identity is 1 because the group generated by 1 has 1 element. The order of 1, 2, 3 is equal to the order of 1, 3, 2 is equal to 3. And these, because the group generated by those two has order 3, and the order of 1, 2 is equal to the order of 1, 3 is equal to the order of 2, 3 is equal to 2. So that's another problem on the test. It will be on there. Once you find the cyclic subgroups, you find the order. So just the size of the subgroups. So this has order 1, order 3, order 2, order 2, order 2. And just real quick, we should note that we know that those should divide the size of the group. So we want to make sure 1, 2, and 3 each divide 6. They do, so that gives us an idea that, yes, that makes sense. That will work out. All right. So now, there's our 5 cyclic subgroups. We have our orders. Now that we have our 5 cyclic subgroups, what do we need to do is try to find subgroups that aren't cyclic. So what am I going to do is I'm going to try to use 2 generators at a time. So let's use, now if I use 1, that's already in each of these, so it's not going to add anything. So I could do something like 1, 2, 3, and 1, 2, 3, 2. They're already in the group generated by 1, 2, 3, so that's not going to become a new group. So what I'm going to do is take, say, 2 of these and see what happens. Or this one and 1 of these and see what happens. So let's just say, what is the group generated by 1, 2, 3, and 1, 2? Well, actually, we can very quickly see we don't necessarily need to find all these compositions because we know that the group generated by 1, 2, 3 has 3 elements in it. So therefore, the size of this has to be at least 3. Plus, we're going to have this one in it as well, so it's going to be at least 4. So if there are at least 4 elements in this, there are 6 elements in the group total. What do we know about the size of any subgroup is that it has to divide the size of the group. So if there's at least 4 in here, and the size of this has to divide 6, well, the only possibility is that the size of this is 6. So we already know that this has to be all of S3. I'm trying to save you guys some work there. So the idea is that if I know that, well, there's 6 elements in here, there's at least 4 elements in here, and it has to divide this. Well, 4 does not divide 6. 5 does not divide 6. 6 does, but that would be all of them. So once I have 4, I have to have all of the elements of the group. So I don't actually have to find this. I know that this is just going to generate S3. Is that okay with everybody? Again, that was Lagrange's theorem that the size of a subgroup has to divide the size of the group. The same thing if I switch 1, 3 in here, I'm going to get the whole thing. 1, 4, or 2, 3 rather, in here, I'm going to get the whole thing again. So if I take this with any one of these, I get the whole thing. So I'm just going to say S3, or the whole thing, is a subgroup of itself. Now I'm going to look at 2 of these at a time. So let's say 1, 2, and 1, 3. And so I know I'm going to have 1, 2, 1, 1, 3, 1. And so now if I look at that set, I know that those 3 elements are in there because I know that everything generated by this and everything generated by this is going to be in there. So I get 1, 1, 2, and 1, 3. Now, I do have 3 elements there, so it's possible that's a subgroup, but I want to make sure it's closed under compositions. So these 2 are fine, these 2 are fine, but if I compose 1, 2, and 1, 3, I get, well, 1 goes to 3, 3 goes nowhere, so 1 goes to 3. 3 goes to 1, 1 goes to 2, so 3 goes to 2. 2 goes to 1, so I would also get the element 1, 3, 2 in here. But notice now that I could go through and finish that, but since I already have 4 elements, I know that this again will be the whole thing. So instead of having to find the rest of these, I can just say, oh, this is going to be S3. So able to answer your question, we know that the order of S3 is 6, so the subgroups have to have order of a divisor. So the only possibilities are having order 1, order 2, order 3, or order 6, but we don't know how many subgroups they're going to be until we actually find them. We don't even know if they're going to be subgroups of order 2 or order 3 unless we find one of order 2 or order 3. There does have to be a subgroup of order 1 and order 6 because order 6 would be the whole thing and order 1 would be the trivial group. But the other ones we actually have to go through and find manually. And so we don't know how many they're going to be until we're done. But what we do know is that we can't have any groups of order 4 or 5. So once we get that there have to be 4 elements in a subgroup, well, the only or 5 elements in a subgroup, the only possibility then is that we'd have to have all 6 in there. So we can save a little bit of work. So if I had a 10 element subgroup, and I had 6 elements in my, if I had a 10 element group, and there were 6 elements in my subgroup, I know that all 10 of them have to be in there. I also know that I can't have a group of order 4, so either if I have 4 elements in there, either there's going to be 1 more and I have a subgroup of order 5, or I'm going to have the whole thing. So knowing that I have to have those sizes is just helping me from having to find all these compositions just to realize it's the whole thing. But we can't beforehand conclude how many are there going to be, or if they're going to be some of each size, or how many of each size they're going to be. So for example, we have one subgroup of order 3, but we have 3 subgroups of order 2. So there's no general rule there. All right. So now I saw 1, 2, and 1, 3 generated the whole thing. If I take 1, 2, and 2, 3, that's going to generate the whole thing. 1, 3, and 2, 3, I'm going to generate the whole thing. So if I take any two non-identity elements, I'm going to get the whole thing. So what we see in this case is that our subgroups are exactly just the cyclic subgroups and the whole thing. Because as soon as I try to have two generators, I generate all of S3. So I will have, in this case, 1, 2, 3, 4, 5, 6 distinct subgroups. And those will be my distinct subgroups. So I found all subgroups. I found the order of each of the subgroups. I think the other thing they wanted us to do is to put this into a subgroup lattice. So what the subgroup lattice means is I just want to think about what contains what. Well, notice that this subgroup is contained in all of these. So when I'm drawing this, what wants to happen is I want this below all four of these, and I want an arrow going down from this one to this one, this one to this one, this one to this one, this one to this one. Also, S3 contains everything, so I want everything to be below S3 and an arrow from S3 that can work its way down to everything else. If there were any other things included, any other of these that were subsets of the others, I'd want to include that as well. But notice that this is not a subset of this, and this is not a subset of this. This is not a subset of this or this. And so none of these are subsets of each other. So we'd call these all incomparable. They're just, you don't have anything going on. There's not a subset here, a subset here. So there should be no lines between any of these four. So if I'm going to map that out, what I'm going to do is I'm going to put S3 up top. So that's the whole thing. The group generated by 1 at the bottom. And then I'm going to have the group generated by 1, 2, 3. The group generated by 1, 2. The group generated by 2, 3. Or 1, 3. And the group generated by 2, 3. So I put these all on the same line because they're incomparable. Each of these contains the trivial group, so we have lines going down. And these themselves are each contained in the entire group, so we have lines going down. And notice that if I follow a line transitively, I get that the trivial group is contained in S3. So this would be the subgroup lattice of S3. It gives you all subgroups and how they all fit within each other. Questions on that one at all?
I have a question about the left and the right cosets. Can you say one more time, please?
Sure, T. That's a great question. He was asking about left and right cosets. That's the one question I think the one question. Maybe there's another one that I haven't gotten to. So if I look back at my PowerPoint here, I'll go up to the previous page. And what we've answered so far is we found 1, find all subgroups. 2, determine the order of every element of G. And since I had all subgroups, I found the subgroup lattice of G, which was number 5. However, I haven't done 3 and 4 yet. So the next thing we need to do is find the left and right cosets for each of those groups. So again, I'm going to need my Cayley table for that. So there we have it set up, and we can go back to the chalkboard with that. So I'm going to start off with, I have to do that for each of these groups. So 1, 2, 3, 4, 5, 6 groups. I have to go through and find the left and right cosets for each of those. So the right coset would be, I'm going to start with S3 because that's an easy one. So let's take some element in S3, and I would say, okay, 1. What is S3, 1? And this would be a right coset because my element's on the right. And so what I want to think is, what does a set S3 with 1 look like is, well, I'm going to take all the elements of S3 and compose with 1. And so I would have, it's hard for me to point at the Cayley table, but the idea is that I had 1 is now on the right, and I have each of these elements 1 through 2, 3. So if I look at the first column, that's going to be 1 composed with 1 is 1, 1, 2, 3 composed with 1 is 1, 2, 3, 1, 3, 2. And so if you guys are looking at the Cayley table, which is down there at your bottom left, I'm really just looking at the first column there is going to be the right coset of S3 by 1. And so that's going to be the set 1, 1, 2, 3, 1, 3, 2, 1, 2, 1, 3, 2, 3. So what I get is just, instead of having to write those all over again, I just get all of S3. If I find S3 with, say, 1, 2, 3, I want to do the same thing, except for I'm going to look at the column. Let me see if I can do this. Something like this. No, that's going to be terrible. All right, so we're looking at the second column because we want 1, 2, 3 on the right. So we're going to take S3 composed with 1, 2, 3, and we're going to read off that whole column because we want all of S3. So 1 composed with 1, 2, 3 is 1, 2, 3. Next, we're going to get 1, 3, 2, 1, 2, 3, 1, 2, 1, 3. So I know it's in a different order, but we do get all 6. So we just get S3 again. And actually, if we do that for every single one of the elements, what we're going to get is that S3 composed with, say, A, for any A in S3, is just equal to S3. So all of the right cosets would just be the entire thing. All right, what would the left cosets look like? Well, they'd be all the sets of the form 1, S3, which would be equal to, well, this time this is going to be on the left, so we're taking the 1 over here on the left-hand side, and then we're multiplying by all of the things in S3, so we're actually reading off here the first row. So the first row of our Cayley table is 1, 1, 2, 3, 1, 3, 2, 1, 2, 1, 3, 2, 3. So again, we're going to get S3. And actually, if I do this one, I'm going to get also A S3 is also equal to S3 for all A and S3 is equal to S3. A is equal to S3. So what are all the left and right cosets? Well, for the S3, all the left and right cosets are just S3. So I would say all the left cosets of S3 are, or is, left coset of S3 is S3. The right coset of S3 is S3. And so if you want to be more precise, you could say something like S3 times 1 is equal to 1 times S3 is S3. So all the left and right cosets, that's the only possibility. That's what we end up with. Any questions on that one? All right, on the other extreme, let's suppose I'm going to say H is equal to 1. Just so I don't have to keep writing the group generated by 1 over and over again, I'm just going to call it H. So what I want to do is I want to find the right cosets first. So the right cosets are going to be all the things of the form HA, such that A is in H3. So an example would be H times 1. Well, if I take H times 1, what I want is 1 is on the right. So again, if I look at my Cayley table, I want 1 to be in the column, so I'm going to look at the first column where I have a 1. I don't know if I'm lining this up correctly. But then I'm going to look at the rows that correspond to every element of H, but the only element of H is 1. So I'm just going to look at what is 1 composed with 1. Well, 1 composed with 1 is 1. So the right coset of H by the identity element is just the identity element as a set, or just H. Then I'm going to continue on and say h times 1, 2, 3. Well, in this case, what I'm going to do is 1 is still on the right. So I'm going to look at the column that corresponds to 1. And then I'm going to look at, well, I'm sorry, 1, 2, 3 is on the right. So I'm going to look at the column that corresponds to 1, 2, 3. And on the left, I'm going to look at all the rows that correspond to h. So that's just 1. So I'm going to find 1 composed with 1, 2, 3 is 1, 2, 3. So this set is just 1, 2, 3. So h1, 2, 3 is just the set 1, 2, 3. All right. What is h132 going to look like? Can you guys help me out with that one? Well, this is just the identity. So the identity times 132 is just 132. And I could go h12 is 1, 2. h23 is 2, 3. And h13 is 1, 3. So how many cosets am I going to have of the group generated by the identity element is I'm going to have 6 distinct right cosets. So you would have to actually write out all 6 of those and say, okay, if we take the group generated by 1, then the right cosets will be the h times 1 is 1, h123 is 1, 2, 3, and then I would list these all out. You also have to find the left cosets. But if you do find the left cosets, you're going to notice they're exactly the same. So you wouldn't necessarily have to rewrite all of that, but you would have to say that, for example, 1h is equal to h1 is equal to 1. 1, 2, 3h is equal to h123 is 1, 2, 3. 1, 3, 2h is h132 is 1, 3, 2. And so I'd have to write out, okay, I'd write that out for all 6 of them so that these would be the left cosets. And you'd have to say the right cosets are given by these. The left cosets are actually the same. And so I have the left and right cosets for the group generated by 1. Very good, James, Abel, and Roberto. HA is just A, H is A for all of those. All right. So now, the whole thing, all the left and right cosets is just the whole thing. And if we start with the trivial group, the left and right cosets are going to be equal, or just whatever element we're multiplying by. We do get more interesting things if we look with the other ones. So I'm going to say, let's look at 1, 2, 3. So if I take h times, now notice that if I take h times 1, I'm just going to get h. And if I take h times 1, 2, 3, notice that h is closed under composition. So if I take something in h and multiply by 1, 2, 3, which is in h, I should, by definition, get something back in h, right? So what I'm going to get here is just something back in h. And so h132 is also going to be h. I will let you guys work through that one on your own, but you can actually line up the columns and the rows. But the idea is, since I'm multiplying by something in h, I'm just going to end up back in h. So the right cosets with all the things in h just end up being h. And by the same argument, the left cosets are going to be the same, because they're all just h. So I am going to focus, though, on what does h12 look like. So again, here I'm going to refer to my Cayley table, and what I want is I want this to be on the right, and I'm going to take all the elements of h on the left. So I'm going to take 1, 1, 2, 3, 1, 3, 2, and I'm going to look at the column corresponding to 1, 2. So if I actually write these down from my list, I get 1, 2. 1, 3, and 2, 3. So I'm just copying those right from the Cayley table I already have. So what that means is if I take an element of H and multiply by 1, 2, I can either get 1, 2, 1, 3, or 2, 3. So I'm going to get 1, 2, 1, 3, and 2, 3. So I actually went through and calculated that by multiplying. This is on the right, these are on the left. This is my column, so I look at these rows, and the corresponding elements are these three, so I end up with this. Now, what I do want to be careful here is, remember that the cardinality of this group was 3, so therefore, each of the cosets have the same cardinality as the set itself. So notice this coset has cardinality 3, H has cardinality 3, they have the same cardinality, so that makes sense. Again, it's just I'm using those theorems that we had to check my work to see if my work makes sense. That looks good, so that is one of my right cosets. And then I can move on and do H23, and if you do that one, you get exactly the same thing. And if you do H13, you get the same thing. So I would say this is equal to H13 is equal to H23. And so we have two right cosets. We either have H, or we have H23 is H13 is H12 is 1, 2, 1, 3, 2, 3. So if you're going to write this up, you could just say, I would just say this is equal to this is equal to this is equal to this. And this is equal to this is equal to this is equal to this. So those are the two right cosets. For the left coset, we did with H already, but we'd also have to do, so these are right. And if I want to do left, I'm going to then take 1, 2 times H. So in this case, what I'm going to get is I get 1, 2 on the right, and then the columns are going to correspond to the 1, 1, 2, 3, 1, 3, 2. So if I write that down as per my Cayley table, I get 1, 2, 2, 3, 1, 3. So this is my set. It's just 1, 2, 2, 3, 1, 3. And so what you'll notice is actually 1, 2, H is equal to H1, 2. And if you follow through, 2, 3, H is equal to 1, 3, H is equal to 1, 2, H is equal to this set here. And so in this case, the left and the right cosets are the same. So the right coset of 1, 2 is the left coset of 1, 2 is the same for every element in here. The left and right cosets are always the same, and as they were for the last two ones. So that is something to note, although I don't explicitly ask if that's true on the test. I just want you to list these. All right, let's move on and say now H is the group generated by 1, 2. So what I'm going to have to do is, again, find my right cosets. So if I take H times the identity, or H times 1, 2, notice because those things are in H, I'm again just going to get things in H. So I get out H. So I have to try other ones like H, 1, 2, 3. So to find this set, notice that 1, 2, 3 is on the right, so I'm going to make the column 1, 2, 3. On the left is 1 and 1, 2. So I'm going to find what corresponds to these in the Cayley table. So 1 composed with 1, 2, 3 is 1, 2, 3, and 1, 2 composed with 1, 2, 3 is 2, 3. So this would be the set 1, 2, 3, 2, 3. And then I can find H of 1, 3, 2, which is going to be 1, 3, 2. And if I read off 1, 2 composed with 1, 3, 2, it's going to be 1, 3. And then I already know H1, 2, so I have to do H1, 3. So that's going to be 1, 3. And 1, 2 composed with 1, 3 is 1, 3, 2. And then H composed with 2, 3 is going to be 2, 3, and 1, 2, 3. And so if you wanted to combine that together, you could say H1, 3 is equal to H1, 3, 2, and H2, 3 is equal to H1, 2, 3 is equal to 1, 2, 3, 2, 3, or 1, 3, 2, 1, 3. So those would be the right cosets of the group generated by 1, 2. To find the left cosets, we go through the same thing. And then 1H is going to be 1, 2. H is just going to be H for the same reason. Anything in H times anything in H is back in H. So we get that is the left coset for those elements. And then I would find 1, 2, 3. H is going to be the set consisting of, well, I'm going to take 1, 2, 3 composed with 1 is 1, 2, 3. And 1, 2, 3 on the left composed with 1, 2 on the right. So I'm reading off my Cayley table here. So that would be row 2, column 4 is just 1, 3. And then if I read off 1, 3, 2H is going to be 1, 3, 2. And then 2, 3. And actually, if I find 1, 3H, it'll be 1, 2, 3H. And 2, 3H is going to be 1, 3, 2H. And so those would be the left cosets. Now, finally, I do want to point out, notice that 1, 2, 3H is not the same as H1, 2, 3. So this is not the same as this because 1, 3 is not equal to 2, 3. So we finally do have a case where the right cosets and the left cosets aren't actually the same. So it is fully possible that the left and right aren't the same. And here would be an example thereof. We just hadn't run into that yet. But that would be 1, 2. Here's the right, here's the left. Now, if you do that for 1, 3, it's going to be a very similar experience. You just, instead of 1, 2, you plug in 1, 3, and then you do 2, 3. You're going to get a very similar thing where you're going to have two distinct left and right cosets, and the left cosets and right cosets will not be equal. And so that's what that will end up looking like for those. So I'm just going to let you say, I actually have this written up as well on the web page, so you can look through all the details of those. But I kind of went through one here to here. If you want to go through another one, let me know. Otherwise, I'm just going to leave it at there for the left and right cosets. Does that make sense to everybody? Notice that for those, there is a lot to write down. So you do actually have to go through those calculations and write out what your solutions are going to be as per the test, so that I can see that you're able to find each of those left and right cosets. Since we had, how many were there? 1, 2, 3, 4, 5, 6 different subgroups of S3. That means you'd have to do the left and right cosets for all 6 subgroups. So it is a lot of actually working through and writing each of those things down. But the process is, I'm really just reading off of my Cayley table. I find the elements of H on either the right, on the columns or the rows, depending on if I'm doing left or right, and I read off the resulting compositions and find the set that that gives me. All right. Now, if you guys have any more questions, I'm happy to answer, but if we actually look back at the test, that is all the questions I'm going to give you on the test. So I told you I wasn't going to do number 6 there because we haven't talked about homomorphic images yet. I meant to delete that from your practice review, but I missed it. So you'll have a group, whatever it happens to be. You'll have to find all the subgroups, the order of every element. At that point, you could do the subgroup lattice, but then you also have to find the left cosets of each of the subgroups and the right cosets of each of the subgroups. So notice that this is only one problem on a take-home exam that you have 2 days to do. I know that there's a lot of work to do in there. There's a lot of factoring, or not factoring, but multiplying out or composing out different things and seeing what all the sets are going to be. So I thought that seemed like a reasonable request for you guys to do over the next 2 days to show that you're kind of catching on to everything that we've been talking about. So if I take a group, what are all the interesting things about a group that I want to know? And these are the interesting things that we've found so far. There are many more that we can talk about in the future, but that's kind of what we want to do, is take a group and break it up into its parts, its subgroups, and talk about what all of that stuff looks like. All right, any other questions then before I let you guys go? James, the take home is already on Blackboard. I just haven't opened it up to you guys yet. I have it scheduled at 3:30, but I'm actually just going to go on the backboard and make it available right away. So it's already posted. I just have to make it available. And so I'll do that as soon as we get done here. So probably within the next 5 minutes or so. And like I said, the only thing that's going to be different is number 6 here won't be here. And then it's going to be a different group. Any other questions? Yes, Nicholas, you are allowed to use your book. Notice a lot of the stuff that you're doing here is calculation based and running through. So I want to see you kind of write that stuff down. So if the answers are explicitly written in the book, don't just copy them and write them down. The answer to the one I gave you is not explicitly written in the book, but please don't go look up online and just find the answers and write them down. I do want to see some of the calculations that you're doing so that I can see that where you're getting things from, so that I can make sure that you understand, okay, well, these are the subgroups and this is how I found them. And so show me that work. It's a take home, so you're allowed to look at whatever you want, but I do need to kind of see where those things are coming from because it is a take home. If there was proofs involved here, it would be things like you can look at the book and you can even use the theorems in the book. You just have to then state which theorem you're going to use. But here it's really just a constructed thing. So I just want you to find these subgroups, write out what they are. So you're more than welcome to look at the book and use that however you would like, as long as I see your work and I see the answers that you're giving me. Is that clear enough? All right.
Have a nice day.
Well, thank you everybody for joining me, and I hope you have a wonderful day. And I'll get that test posted right away so you can start at your convenience. I'll see you on Wednesday.